Welcome to part 2 of lecture 14 on plutonium chemistry for chemistry 418 radiochemistry. This part of the plutonium lecture is going to focus on the metallic state of plutonium. Metallic plutonium has many interesting properties, all derived from the F element chemistry. The density varies, but can be close to 20 grams per milliliter, and has a relatively low melting point around 600 C. There's strong interest in metallic plutonium related to how it's made, the processing, the relationship between the structure that's produced, and the resulting properties. So this relationship is important for understanding the behavior of plutonium metal. There's also large interest in the reactions of plutonium metal with water and oxygen due to formation of oxides. And there's also studies related to the impact of sulfur radiation. How does that influence the behavior of plutonium metal? Now, plutonium metal can be formed a number of ways, mainly through metal reduction with solutions that are reductive for the plutonium compound. For instance, plutonium tetrafluoride can be reduced in calcium metal, where the plutonium tetrafluoride goes to the metal and calcium goes to the fluoride. So this is performed by first producing the tetrafluoride species, inserting it into calcium metal, melting the calcium. When the reduction occurs, plutonium is more dense and it solidifies at the bottom of the crucible. This is similar for the oxide, so the direct oxide reduction with calcium metal can also be performed, where you use plutonium dioxide, calcium, and calcium chloride. And then there's molten salt extraction, where the molten salt system is used as a solvent, where plutonium can be reduced to the metallic state, and the solvent, in this case molten salts, are not influenced by the reduction behavior. Electrorefining is this process where plutonium is formed into a metal in a molten salt system. In this case, liquid plutonium can oxidize from an anode ingot into an electrolyte salt. The salt is at elevated temperature above the melting point of plutonium metal. So the plutonium can be introduced, oxidized plutonium-3. This plutonium-3 can go to the cathode, where reduction occurs, and when the plutonium metal is formed, it melts and it drips off the cathode into a criticality shape, a criticality safe shape, as this ring shown here. Plutonium metal can also be purified through zone refining. In this case, plutonium metal can melt. Some of the impurities will not melt, such as oxides. They'll form a slag. So you could take plutonium metal, you have a melt zone in which the plutonium metal can pass through at a slow rate. The impurities travel in a direction either the same or opposite of the melt, but you wind up having a section of the metal that has a relatively pure plutonium phase and a phase that contains the impurities. Another interesting property of or purification route for plutonium metal is shown here, where you can do vacuum distillation of americium that would be produced from the decay of plutonium-241 in a plutonium sample. In this case, you can levitate plutonium metal in a magnetic field, heat up the sample so it becomes liquid. By putting this under a vacuum, you can distill off the americium and leave behind very pure plutonium metal. This is usually material that's used for experiments. And the reason people would be interested in making pure plutonium metal extremely pure is to study its fundamental properties. Plutonium metal has some extremely interesting properties, particularly the different phases of the plutonium metal. Here we see that the metal goes through 6 phases. This is the length of change plotted against the temperature. We see there's 1, 2, 3, 4, 5, 6 solid phases, a liquid phase. The face-centered cubic is your least dense phase. All these levels are close to each other energetically, so that's why they can be reached through just heating the sample. Then the densities of these phases vary dramatically. The data is shown here, where the most dense phase is the alpha phase, which is close to 20 grams per milliliter, and the least dense phase is this delta phase, this face-centered cubic, the FCC phase, where you get a little bit under 19 grams per milliliter. Plutonium also has an interesting property where it expands when it melts, and it also has a relatively low melting point. The data for the different phases are listed here. Their temperature range, lattice, crystal lattice and space group, unit cells, atoms per unit cell, and then the density. This interesting property of plutonium, where you have the different phases, is also manifest at higher pressure. So in this figure, see, as we increase the pressure, this phase, which isn't present at regular atmospheric pressure, can be formed. And these different phases are really due to the behavior of the 5 F electrons in the plutonium metal. So, for instance, with the alpha phase, the low symmetry ground state is due to this 5F bonding. These F orbitals have odd symmetry, so they're similar to the P orbitals. So you see some similarities between the behavior of plutonium and these P orbital metals, tin, indium, antimony, tellurium. And this has also been modeled with local density approximations. And they show that the narrow widths of the F bands lead to low symmetry ground states of the actinides, which is observed. And here's an example of some of these lower symmetry crystal states. This is similar to the figure that was shown on the previous slide. And we see as we get higher, we go from lower to a higher symmetry. The other thing that can be pointed out here, compared to aluminum, which just has one phase that increases in length, and then when it reaches its melting point, the density decreases. Very simple system. Plutonium is much more complicated with these different phases, and then added to the fact that the liquid is more dense than the highest temperature solid phase. An example of the mixing of different electron orbitals in the development of plutonium metal can be shown here with the delta plutonium, which has the FCC phase. The total contribution is shown in this solid red line. Now, if plutonium was only consistent with the F electron band, the measurement would be, the lattice constant would be smaller than contributed. It would be dominated by here. The contribution from the S and P bands, which are shown here, stabilizes larger volumes, and the F band is narrow at larger volumes. So if we see over here, we see that it gets narrower. And there's strong competition between repulsive S and P band contributions and attractive F band contributions, and this caused some instability near the ground state. One of the manifestations of this instability is that the density of states functions are different for the low symmetry crystal structures. What that really means is that total energies of crystals are close to each other, close enough where they can be expressed by heating the metal or by applying temperature. If you think about it from terms of a Boltzmann distribution, you can start promoting electrons to higher energy states, which from one state to another, so that they can occupy different orbitals, different bonds, different bands, and for the plutonium metal, that's going to manifest itself in different crystal structures. As we mentioned, these F electrons' behaviors change with lattice vibrations or heating, so they can be manifest and reached by just heating the sample of plutonium, resulting in these different phases. And these interactions with temperature result in the phase transformations between the alpha all the way to the other phases that are present. These small temperature changes can induce large electronic changes, and they produce relatively large free energy changes. The kinetics are shown here for the changes of plutonium going from one phase to another. As you can see, these curves that we highlighted show some of the boundary conditions for the kinetics. And as we see here, this is, for example, an alpha phase in an unstable regime and a beta phase in an unstable regime. At a given temperature with a certain time, these beta phases, which are unstable, will start to go to an alpha and a beta phase and then complete over to an alpha phase. And the reverse is true for the alpha going to the beta. This behavior is all related to the mixing of the different orbitals that can be occupied in the plutonium metal. This behavior for the actinides increases up to plutonium and then switches over from americium on, where the material is more like the lanthanides. We can see that there's a relatively large gap between the delocalized and localized nature in uranium, localized and delocalized nature in americium, and we get a mixing of the localized and delocalized behavior in plutonium. So because of this, we get these transitions. The itinerant here is the stable phase. Over here we get a mixture of going it from delocalized to localized, where in the americium the F electrons are more localized. And then here's fundamentally the fraction of 5F electrons involved in bonding. As we see, we start off with the alpha phase. As we would see here, we have largest amount of itinerant behavior. Right, so the F electrons are involved in bonding. We get a decrease as we go down. We go to the least dense phases, have the lowest amount of F electron contribution in the metal bonding, and we actually go up when we hit the liquid phase. Another way of viewing this behavior in the F element behavior in the actinides is shown here. As we go from neptunium to plutonium, we see the phases get more complex, and then as we go beyond plutonium, the F bonding decreases and the phases become much simpler. This is also observed here, where we get simple phases. We start increasing, we go up to plutonium, the phases become more complex. We're increasing the F orbital behavior and F orbital interactions in the materials. And then once we get beyond plutonium towards americium, the systems becomes much simpler. So for plutonium metal, we see that the liquid is denser than the 3 highest temperature solid phases. So liquid density is 16.7 grams per milliliter, where the other phases, the 3 highest temperature phases, are less than that. For this reason, materials that are made with plutonium are often alloyed so that behavior can be consistent. And here's an example of figure showing the phases as a function of temperature for plutonium metal and a plutonium alloyed with gallium. We see that the gallium phase, the delta phase, is stabilized over a very large regime. Lattice change or length change is minimalized when temperature is reached, where the epsilon is formed, and then liquids are also formed. And we see that there's consistent behavior with these alloys. And as an example, though, this phases that we see here is a relatively narrow band of the plutonium-gallium phase diagram. We see that the alloy only occupies a relatively small area of this phase diagram, where we have fundamentally 11 different compounds that can be formed between plutonium and gallium. So it's a rather complicated phase diagram, but this property here is exploited for plutonium metal. And as we see here, this is the example of the change in the density as the material temperature increases, we see a change in density where the liquid phase winds up being more dense than the solid. Some details of the gallium-plutonium phase diagram are shown here at the low gallium concentration end, and these are the US and Russian phase diagrams. The information is shown here. The main difference is that the Russians observed complicated intermetallic, so plutonium alpha phase plus this plutonium-gallium intermetallic, under conditions where the US phase diagram just predicted a single delta phase. Both these phase diagrams are just extrapolations, but they have very different conclusions, and these were important differences where at the end of the Cold War they were used as a common research project to understand the behavior of plutonium gallium alloys under these specific conditions. Plutonium also forms alloys with a number of different metals, such as these listed here can stabilize the delta phase at room temperature, and these listed here, some of the tetravalents. The delta phase can be stabilized with rapid cooling. The neptunium stabilizes the alpha and beta phase region, and the beta phase can be stabilized at room temperature with hafnium, titanium, zirconium, these tetravalents. Again, with rapid cooling, you can stabilize the delta phase. As an example of the large delta phases that can be stabilized, over here is shown the delta phase for the alloys of plutonium with americium. The FCC phase is stabilized. Compare this to the delta phase stabilization by the gallium. It's relatively large for the americium, relatively low for gallium. Plutonium can also form eutectics, in other words, where the melting point of the combined materials is dramatically decreased. So here's an example of the melting point of plutonium metal. Here's for iron. The eutectic is at a lower point. And plutonium can make eutectics with iron, cobalt, nickel, those components of stainless steel. If stainless steel is used as cladding and plutonium is produced in the uranium of fast reactor fuel, you may have to investigate the formation of eutectics in this material. There's also interstitial compounds that can be formed in plutonium metal, such as oxygen, carbon, nitrogen, and hydrogen. They get placed within the interstitial atoms. They form interstitial atoms within the lattice of plutonium metal. The electron configuration of metallic plutonium is shown here, where you get a mixture of F, D, and S orbitals. From calculations, all 8 valence electrons are in conducting bands. The 5F electrons in alpha plutonium behave like 5D electrons of transition metals, more so than the 4Fs of the lanthanides. And this is what really manifests the behavior. The 4Fs are not really involved in the bonding and structural behavior. They're not in the highest occupied molecular or highest occupied orbitals, whereas in plutonium the 5Fs are. The bonding and anti-bonding orbitals from the sums and differences of the overlapping wave functions are complicated for the actinides. And again, the small energy differences between the orbitals can overlap in the solids, and this is what accounts for the different configurations, and it's just manifest for the actinides at plutonium metal. Some of the methods for understanding and modeling plutonium metal are briefly described here. Density functional theory has been used. For the actinides, one needs to include low symmetry structures, relativistic effects, and electron-electron correlations. Local density approximations have also been used, and these include some potentials and Coulomb interactions. And then there's a generalized gradient approximation. These are localized electron density and density gradients. All these terms are often employed if you read papers related to density functional theory, DFT computations involving the actinides. these terms will be used. The computations are used to calculate energies at the ground state and can be compared with different configurations to identify those ground states which should be the most stable. So plutonium has the right amount of F electrons for this chemistry to be significant. One of the influences of the heavy nucleus of plutonium and the actinides are to impart relativistic effects on these F electrons. What's the manifestation of relativistic effects? It's due to the fact that particularly the s orbitals are pulled closer to the nucleus, since they can have a probability of being at the nucleus. They experience more of the charge of the nucleus. Their velocities increase. They become relativistic. Their relative mass increases. They have their radii shrink. This shields the F and Ds primarily from the charge of the nucleus, and the the D and F orbitals get extended. So we can see this behavior here, where if we examine the 4F in trivalent samarium, where the dashed line here is the relativistic calculation, the non-relativistic calculation, the solid line is the relativistic calculation. We see there's a slight extension on the relativistic, but if you compare that to the plutonium, the isoelectronic plutonium, you see that the relativistic calculation is further extended to the point where an area where the distance is important for bonding, you will get F electron contribution. So these relativistic effects allow 5F electrons to participate in chemical bonding because they're relatively far from the nucleus compared to the 4Fs. And if we look at the 4Fs here, by this point, so let's say 1.5 angstroms, very little probability of finding them at those 4Fs at this point, where we have a much larger probability of finding the 5Fs. As we mentioned at the beginning of this lecture, the physical properties of plutonium metal are of interest. And once the metal is made, we get some metal mechanical properties, particularly stress strain. The alpha phase plutonium is strong and brittle, similar to cast iron, as we see from this point. Cast iron plutonium metal shown here, where the delta phase shows this limited elastic response followed by plastic behavior, basically the same sort of behavior as aluminum. The delta phase has something low yield strength and ductile fracture. So the properties of these two phases are radically different. As we see with the alpha phase, it's more like cast iron, where it would just fracture after putting a certain amount of stress onto it. It wouldn't bend very much, whereas the delta phase would act more like aluminum. It would start to, after a certain amount of stress, it would start to increase. It would start to increase in length. So an example, for those of you who have not seen stress-strain relationships, is shown up here. The influence of temperature on the strengths of plutonium phases have been examined, and it's found that the alpha and beta phases are very sensitive to temperature, as we see that the stress changes dramatically as a function of temperature, where the gamma and delta phases over here less pronounced, less of a pronounced change. Now, the ranges are fairly wide, and this is a compilation of different work, and there might be some variations in the behavior and properties of the materials, particularly for the alpha phase plutonium. That's why we get such a large range. But what we do see as what's consistent is this large change in stress as a function of temperature. So 100 degrees, we go from something on the order of 100 to 400 megapascal, where for the gamma and delta phase, over 100 degree for the delta phase, we hardly get any stress change. So plutonium metal has an elastic response. This is again due to electron structure and resulting cohesive forces. Metallic bonds, when they interact, they tend to have high cohesive forces that give high elastic constants. Now, metallic bonding is not very directional, right? Since these electrons that these metal ions are sharing should be shared throughout the lattice. So this results in metal atoms that surround themselves as many neighbors as possible, so they're close packed and relatively simple structures. Now, as we've already seen with the plutonium 5F electrons, they have relatively narrow conducting bands with high densities of states. So plutonium has typical metal properties at elevated temperatures or in alloys, as we've seen, but for the lower temperatures we have this low symmetry. And again, this not only has this structural behavior, but has some of these mechanical behaviors that go along with it. And again, it's all linked to the behavior of the F electrons. Now, one of the investigated properties of plutonium metal is this corrosion relevant oxidation. This mainly has to do with the fact that the metal itself is very dense, the oxides are less so, so any corrosion or oxidation is accompanied by swelling of the material since the density is decreasing. What's been examined is formation of oxide layers, how these oxide layers form, and the role of water and oxygen in the atmosphere on the corrosion and oxidation of plutonium metal. Plutonium metal has pyrophoric properties, so it's known that the oxidation can be very rapid. What is known is that the corrosion depends upon the chemical conditions of the plutonium surface. So if there's low amounts of oxygen present, as opposed to forming UO2, Pu2O3, so the trivalent as opposed to the tetravalent oxidation state can be formed. This phase actually promotes corrosion by hydrogen. So the role of water, again in the presence of oxygen, is important. Another thing is the formation of the hydride can increase the oxidation of plutonium in oxygen by 10 to the 13th. So a small amount of hydride formation, for instance from water, can have a very pronounced effect on any oxidation of the plutonium. There's also a hyperstoichiometric dioxide that can form in the presence of water, and this can enhance the corrosion of plutonium metal in moist air. Here's an example of plutonium oxidation in dry air, where we have O2 sorbing onto the plutonium surface. This forms an initial oxide layer. Over time that oxide layer grows, and then we have diffusion of the oxygen through that layer in order to oxidize more of the plutonium metal. During this process, through the oxidation, heat occurs. It's an exothermic reaction. Over time, this oxide layer can grow. When it gets to around 4 to 5 microns in room temperature, there's surface stresses that occur, and the oxide layer starts to fall apart. So once that occurs, this area now has a shorter path length. This can lead to further oxidation. Over time, the oxide thickness becomes constant due to this behavior. The kinetics of this system vary slightly from the overall picture, where a thin layer of the trivalent plutonium oxide forms. Here we see what we discussed in the previous slide, this O2 reacting with the plutonium forming the dioxide, O2 penetrating, and then we get this small layer of Pu2O3, and autoreduction occurs where the plutonium tetravalent state reacts with the plutonium metal. You oxidize some of this metal to this trivalent state, and eventually the oxygen that diffuses through interacts with this Pu2O3, forming the PuO2 state. As we see here, this layer is involved in the kinetics of the formation of this oxide. The oxidation kinetics of plutonium metal and alloys have been examined in a number of conditions, primarily dry air and water vapor. The data shown here, and what we have is the log of the reaction rate R versus 1 over T. So the slope of these is proportional to the activation energy for the corrosion reaction. Curve 1, shown here, this is just the oxidation rate of unalloyed plutonium in dry air or dry dioxygen at atmospheric pressure. We see that this overall rate is between these values here and these values here. This other curve, where the rate is where we have our rates higher at the same temperature. So as we see here, 100 degrees, 200 degrees, this is the inverse of the temperature down here. We see that this includes water vapor up to 0.21 bar. We see that this has been examined over a few temperature ranges. The behavior is consistent for temperature ranges up to 110. Then from 110 to 200, we see this change occur. But overall, the rates are going to be larger at the same temperature than for systems with dry air. So the role of water definitely increases the oxidation. This is the behavior of the gallium stabilized delta phase in dry air and moist air, respectively. And we see that those oxidation rates are lower, so the alloy has a little bit better stability against oxidation when compared to the metal. Now, if we look over here at this curve, this is a transition. It's between, at higher temperatures, we start to see an autothermic reaction, and this is the transition zone. So these rates, higher temperatures, the rates are definitely getting higher. And over here, we see that there's a temperature-independent rate. Right? As the temperature increases, the rate remains constant. And this is for the reaction of burning metal or alloys under static conditions. And then if we do an experiment where you would you'd have droplets of the metal or alloy that were burning during a free fall, you would actually increase the rate with temperature. So the data from this curve demonstrate the role of water in the oxidation and the fact that the alloys are less susceptible to oxidation than plutonium metal. Here's an overview of plutonium metal oxidation under various conditions. Here's what we described earlier, where we just have air atmosphere at 25 degrees, where we have the plutonium dioxide, the trivalent oxide, then with the plutonium metal. If the atmosphere is varied, and we have either inert gas or dry air, what we see at 25 degrees over a long period of time is an increase of the growth of this Pu2O3 layer. Under dry air, it's a very thin layer. However, under the inert atmosphere, this layer grows into a rather large, it can be a rather large layer. If the temperature is increased, what we see occurring is for both systems, the Pu2O3 layer can be very large. In the dry air, it goes to a steady state, whereas in the vacuum and inert gas, this phase can be the dominant oxide phase. We can also examine the oxidation of plutonium as a hydride species. Here we see the rates for the oxidation of plutonium hydride that's coated plutonium, and this oxidation is done in air, a hydride of plutonium, or the 3 oxidation state 3 oxide coated plutonium in hydrogen. So in other words, this is a formation of the hydride. And then here's the plutonium hydride coated plutonium in oxygen. So we see that these rates, particularly if we compare them to the rates we previously discussed, we see that there are a few differences. One, the rates are a lot greater. And two, they're constant. We don't see the temperature variation as we saw with the previous discussion on just the metal oxidation. So the hydrides are definitely a system that one would want to avoid. This is one of the reasons that water is effectively removed from any stored plutonium metal. And as we see here, this hydride is readily oxidized by air. And then if we go from an air to an oxygen atmosphere, the rate of oxidation goes up. And this hydriding occurs only after the dioxide layer is penetrated. So the hydrogen is kind of an initiating step. We see that these values are constant. And one of the things that we could take away from these constant values is that the surface acts as a catalyst for the oxide reaction. So the hydride, it's not a true catalyst. It is fundamentally destroyed, but then the hydrogen migrates and then reforms the hydride later. We'll talk about that in the next slide. And these are obviously, from these rates, we see that these are the most reactive locations. In fact, from temperatures between negative 55 Celsius and 350 Celsius and a hydrogen atmosphere of 1 bar, the reaction is fully active. It consumes plutonium at a constant rate between 6 and 7 grams per centimeter squared per minute. And this means that if you had an alloy of plutonium or an alloy of plutonium metal or plutonium alloy, the rate of this oxidation would be about 20 centimeters an hour. And here's more detailed about the oxidation plutonium hydride as we just discussed. So imagine that we have a hydride coated plutonium oxide that gets exposed to oxygen. The oxide reacts with the hydride, forms this plutonium-3 oxide. With the evolution of heat, this forms at the surface. This produced hydrogen then migrates to the plutonium metal layer, where it then forms plutonium hydride. This is an exothermic reaction and helps drive this formation. That's why the kinetics are so rapid. It's almost a autocatalytic type of reaction. The process is that we get oxygen absorbs at a gas-solid interface as the dioxide, as shown here. So this dioxide forms the plutonium-3, the Pu2O3 species. And as the O2 dissociates and enters the oxide lattice as the anionic species, as what's shown here. Then we get this thin layer of we get this layer of oxide, and a thin layer of the dioxide may exist at some sort of surface or some interface, but it's not a dominant species. So as this oxide enters the lattice, we definitely form some oxidation. This migrates down to the hydride lattice area, where we get the formation of the oxide. And the oxygen for this reaction is exothermic, forms the dihydrogen, and that forms the plutonium hydride. So we see that the surface is where the reaction occurs, but we get a migration of both the oxide and the hydride through the plutonium metal. Now, why this is important is that for storage of plutonium metal, it's you want to prevent any sort of oxidation from occurring, because it goes from a very dense material to a lighter material. That means you have swelling, as an example here, of 2 storage containers that contain plutonium metal. Upon the reaction of this oxidation reaction, the material converted from the metal to the oxide and the hydride, swelling the package, and in one case, bursting the package. When you've completed part 2 of the lecture on plutonium chemistry. Please proceed to the third and final lecture.